Hi everyone. Today we're going to talk about ionic binary and continue with nomenclature. These are going to involve charged ions, specifically metals, bonding together with a nonmetal. Ionic compounds occur when a positive ion and a negative ion stick together, much like a north and south pole of a magnet will stick together. The atom that loses its electron is called a cation. It has a lower electronegativity, if you remember us talking about that earlier in the year, and it readily gives away its electrons, giving it an overall positive in total charge. The atom which gains electrons is called the anion, okay? And like I said, the cation loses and the anion gains. And the anion has a higher electronegativity, and it readily takes available electrons, giving it an overall negative in total charge. Now, how I've always remembered these is a silly little cartoon, and I think of a little bitty kitty cat. He is a Plussy cat. He is always happy. He is positive. All right. And this is Angry Ann. I think she's mad because of her really bad hair. But that's okay. And she is negative. So this is just a silly way that I've always remembered these terms. But the real thing is that cations are going to be your metals, and your anions are going to be your nonmetals. Okay? As I said earlier, we're only going to be dealing with binary. Okay, so we're only going to be talking about two elements, okay, a metal and a nonmetal. And again, it doesn't matter how many atoms we're talking about, but we are talking about two elements, okay. The important about using charges for compounds is knowing how big the charge is, though. So we've got these positives and negatives, but we need to know how many positives and how many negatives, all right. And knowing this all comes from our valence electrons. So if we look at our alkali metals, they have one valence electron. Our alkaline earth have two valence electrons. I'm going to skip the transitions for a minute. Our boron group has 3, 4, 5 for nitrogen, 6 for oxygen, halogens have 7, and the noble gases have 8. Okay. And those valence electrons are where we're going to get our charges from. Okay, so let's look at the alkali metals again. Okay, it has one valence electron. Okay, and if you lose one electron, okay, for example, if I have sodium, it has 11 electrons. Okay, sodium has 11 electrons. Okay. If I have 11 electrons, it also has 11 protons. And it is going to readily give away that one valence electron, okay, giving it now 10 electrons. Well, electrons have a charge of negative, and protons have a charge of positive. Have 10 negatives and I have 11 positives. This gives me an overall charge of a positive 1. Okay, so one valence electron, this first column, is going to have a 1 plus charge. Okay, the alkaline earths, 2 valence electrons, they're going to have a plus 2 charge. The boron group is going to have a plus 3 charge. Okay. Now, we really don't have to worry so much about the carbon group, but for our purposes, we'll just say that it has a plus 4 charge. It has 4 valence electrons, be a plus 4. Now, let's look all the way over here on the halogens, okay? They have 7 valence electrons. Okay, for example, if I look at chlorine, chlorine has 17 electrons, a neutral chlorine, and it has 17 protons. In that 7 valence, it wants 8, so it's going to readily gain 1 extra electron, giving it 18 electrons. So that's going to give it 18 negatives and 17 positives, giving it an overall of a -1 charge. Okay, so my halogens are all going to have a -1 charge. My oxygen group is going to have, with 6 valence, it needs 2 more to get to 8, so a -2 charge. And my nitrogen group is a 5 valence, so it needs 3 more to get to its 8, so it's going to be a -3 charge. Okay, so you should always remember those columns. So again, +1, +2, +3, +4, -3, -2, -1. All right, so that's something you always have to remember. Now, it is important to say, it's worth noting, that charges and oxidation numbers are written differently, and some of your teachers might have you writing these with net ionic equations and net ionic formulas. And the proper way, if I were going to write magnesium with a +2 charge, the proper way to write that would be Mg2+, and it has an oxidation number of +2. All right, now I tend to just write all of my numbers backwards, but how your teacher wants you to write them, make sure that you're doing it that way. Okay, so there is a proper way to do it, and make sure that you are doing it that way. Okay, and last thing is, we don't need to worry about the noble gases because they're already at an 8, so that's why they don't bond with anybody. They're not going to get these charges back and forth. Okay, so let's look at our first example. We have lithium plus sulfur. Okay, lithium is in that first column, so lithium is going to have a +1 charge, and sulfur is in that 16th column, and it's going to have a -2 charge. And if, like I said, if you're using the net ionic charges to add up to 0 with your teacher, then please continue to use that method. But I prefer an easy shortcut to figure out the number of atoms for a compound. I simply take the exponent of one and put it into the subscript of the other. So I end up with Li2S1, excuse me, not a dot, Li2S1, all right? Now, you don't ever write ones, so you're going to end up with Li2S, okay? And switching those exponents is always going to work, okay? But like I said, if your teacher prefers you to use your net ionic charges and add up to 0, make sure you are using that method, okay? Now let's name it. So to name it, you're going to write down the first element, plus second element plus ide. So my first element is lithium, and my second element is sulfur plus ide. Now you're not going to write sulfur-ide, but you're going to use kind of like roots like you did with your covalent binary. So I'm going to have lithium sulfide. All right, pretty plain and simple. All right, now let's look at magnesium and fluorine. Magnesium is a +2 charge. Fluorine is a -1 charge. You take the exponent of one, put it in the subscript of the other to give me Mg1F2. You don't write 1, so Mgf2. And I'm going to name it, and I'm going to call it magnesium fluoride. Plain and simple. Now, a question I get asked quite often is, how come I don't want to call this difluoride? How come you don't say magnesium difluoride? Well, the only time you use those prefixes is if it is covalent. This is not covalent because it has a metal. So you're never going to use those prefixes in these naming because it's metal, non-metal, not two non-metals. So that di is unnecessary. Okay. Let's do one more example here. Let's do sodium plus nitrogen. So sodium, first column, so +1. Nitrogen, that nitrogen group has 5 valence, so that's going to be a -3. So I'm going to put the exponent of 1, put it into the subscript of the other, so Na3, N. And that's it. We're going to name it, we're going to call it sodium nitride. Your cation, your positive, is always written first. So your metal, your cation, your positive is always written first. So make sure you're always doing that. All right. Now, one thing you do have to watch out for are multiples. And one way you can think of it is in empirical formulas. Okay, you can have your molecular formulas, and your reduced form is going to be your empirical formula. So if I look at calcium and oxygen. Now, if you're using your net ionic totals, your net ionic charges to add up to 0, then this is an unnecessary step because you're not going to have to worry about this. But if you're just switching the exponents, this is something you're going to have to watch out for. Calcium, an alkaline earth, is going to be a +2 charge. Oxygen, and 6 valence electrons, is going to be a -2 charge. And we're going to flip these and put exponent of 1 into the subscript of the other to give me Ca2O2. Now, if you have a formula that can be reduced, just like you have a fraction that can be reduced, you would never turn that in math class. You would always reduce this to 1/2. So if you can reduce these two numbers, you should. If they are multiples of each other, then you should reduce it. Okay, so your final formula would be CaO. All right. Like I said, if you're using net ionic charges to add up to 0, then that's just an extra step you won't have to do. But if you're just switching the exponents, you do need to watch out for that. Okay, so to name it, we're going to have calcium oxide. Okay, pretty plain and simple. All right, now the only thing that I have left to talk about are the transition metals. Okay, so transition metals can be a little tricky if you're not paying attention. Okay, so first off, let's assume that all the transition metals have the same charge as the alkaline earth. So for now, we're going to assume that all transitions have a +2 charge. Okay, the only exceptions to this is silver. Silver is always a +1. Okay, silver is always a +1 charge. Okay, it's never going to be different. But what we're going to talk about is that some of these can be different than 2. The silver will never be a 2. It will always be a 1. Okay. The way I remember this is a little diagonal trick that I've known for years and used. Zinc, it's actually, it never changes as well, but it's always a 2. So zinc is 2, silver is 1. Well, in this column, the boron group, these are 3 valence electrons. Aluminum has a +3 charge. And I always remember this silly little diagonal, 3, 2, 1. Aluminum 3, zinc 2, silver 1. And that little diagonal has always helped me to remember that silver will never change. It will always be a 1. Okay? But sometimes transition metals aren't 2. Okay? Have you ever seen something written like this? Iron 3 oxide. That 3, that Roman numeral, is actually telling you the charge. So the 3 means it is a +3 charge. So oxide, oxygen, is going to be a -2 charge. So when we write this down, flip exponent of the subscript and Fe2O3. This would be iron 3 oxide. Now, not every transition element has multiple ways to write it, but some of them do have 2 and 3 different types of valence electrons. So what you're going to assume is that if there is not a Roman numeral, assume it's a 2, unless it's silver. So if there's no Roman numeral, it's a 2, silver is a 1. Okay, you're never going to have silver Roman numeral 2 because it doesn't exist. All right, let's do another example here. Let's do copper 1 chloride. That copper 1 means a +1. Chlorine is going to be a -1. Put them together, CuCl. Exponents go into the subscripts, and we get a simple formula of CuCl. Okay, and essentially that's about it. Okay, you do need to make sure that you're watching out for the empirical formulas like before. Okay, you could have something along the lines of iron 4 oxide. Okay, so iron 4, that 4 means +4, oxygen -2. I switch my numbers, Fe2O4. Again, if you're using that ionic charges, this is just a step you won't have it'll to add up to 0. But if you can reduce your numbers, make sure you do FeO2. Okay, so make sure you're watching out for that. Other than that, that's about it. You've got ionic binary, you've got covalent binary, and you've now got diatomic elements. So make sure you're reviewing those. Make sure you're always looking at your transition elements to see if there are Roman numerals, and that's telling you what the charge is. And that should be about it. Hope this helps. Next class, we're going to talk about polyatomic ions. And remember, work together, help each other, and make the world a better place. See ya.